Okay, welcome everybody. You already see the title on your screen. The talk today will be about morphologies that are observed in the central region of barred galaxies. This area in the literature is encountered as the innermost kiloparsec, although we do not literally claim that whatever happens in all galaxies is in a radius of 1 kiloparsec, the very central region. And this is a study, this is a topic that has been studied by various authors. The literature is very long. If one wants to consider all papers that have been written on that, it is a long work. So here in the talk today, I will summarize findings that practically come from the work that Stavros Pastras, you all know him, did during his master's thesis while he was here. Of course, there have been some additions and some parts of this work has been worked out during the last years, but essentially is the work of Stavros that he did more than 2 years ago now. So let's start to see exactly what is the topic here. Okay, so I will change here. Okay, here we go. Oh, no, back. Here. Okay, here is an innermost kiloparsec region. You see this galaxy, NGC 1433. And practically what the area that we will discuss today is this one here. So this one here. So at this region, we usually observe a ring, the so-called nuclear ring. And then inside this ring, in some cases, there are substructures that are observed. For instance, in this case, you can see two dust lanes, yes. The size, well, I give the order of magnitude, innermost kiloparsec, let's say. Okay, I don't know exactly if it's 1.2 or 0.8 kiloparsecs, but it's of that order.
And the large thing is 10.
And the large thing is 5, 6, 10 kiloparsecs if you want. Yeah, okay. In this case, I think it is something like about 6 kiloparsecs, the distance from the center to the end of this kind of spiral feature that you see here, straight dust lane shocks, as we say. This is the main bar. Okay, here we observe here the gas. We discuss about how the gas behaves in these cases. We will speak also about stellar response, but mainly we speak about the gas here. So let's say if this one is 6 kiloparsecs here, this distance from the center to the end of this dust lane shock, then this one is of the order of 1 kiloparsec. Okay, this the size of the ring of the ring. Okay, it is not always the same morphology. We observe several morphologies in the central region, in the gas, in the dust, and sometimes whenever we have observations in the near infrared, also we can claim that we see also the stellar component in there. You will see some more examples. Okay. So what I wanted to tell you is that the central region, as regards the nuclear rings, you see many nuclear rings, and people say that here is, as we will say, the area where we have this X2 flow from the X2 family, you know where it is. But there are significantly less papers, less studies dealing with what is observed inside, closer to the center, inside the nuclear ring. There are papers, but not as many as with the nuclear ring. The point is that in the models, for instance, there is a resolution. Resolution is also the problem in the observations. so that one has very accurate morphological descriptions in, let's say, in the dust, in CO, etc. One very extended study was by Martini et al. In 2 papers back to 2003. And they say that obviously the opposite to the previous case that we have seen, they claim that their statistics shows that in most cases the nuclear spirals or whatever it is inside the ring links directly to the relative straight dust lane shocks that are associated with a large scale bar, this kind of straight lines that I have shown you before. And here is an example of what they claim. For instance, here you can see that better in the right image that you have the dust lane shock, the straight line dust lane, something that curves, it comes inside, but in this case we do not have a very well defined nuclear ring. They claim that this is the most frequent case. But okay, there are of course nuclear rings. I don't know how accurate this of this statistics. We have both kind of morphologies all the way down to the center. And another feature that they have classified, there were some tightly wound nuclear spirals, which they have been observed mostly to galaxies that are classified as unbarred. As long as we can find unbarred galaxies, I would say, with very weak bars in the center. Then they have found these tightly wound spirals. You will see examples later. Okay, some people have pushed it very much, trying to observe then deviation from this very grand design, let's say structure, defined grand designs that have been also observed. And here is a famous case, a three-armed spiral that was that it is observed in one of the most typical grand design barred galaxies, 1097, which has also a known black hole, supermassive black hole in the center. Here they find these three-armed spirals. Our friend Fatih et al. Have published several years ago these images, but there are also other authors that have studied this three-armed spiral structure. In conclusion, there are nuclear rings. Inside the nuclear rings, we find some kind of spirals. In some cases, when the bar is not that strong, they are tightly wound. In some cases, the nuclear ring is not to be observed, and then we have a continuation of dust lanes that come from the main bar of the galaxy all the way to the center. Okay, now whenever this nuclear ring is observed, in most cases, it is better to describe it as a pseudo-ring. And we say that pseudo-ring and not a ring because, as you can see in the image of this NGC 5383 galaxy and in the images of the central region of another one, the surface density along the ring is not homogeneous. You find there some parts that are brighter than the two others. And the brighter ones are those that are associated with the continuation of the dust lane shock of the main bar. You can see that in the galaxy, in the case of the galaxy, here is the dust lane shock that goes all the way. Here is what we call pseudo-ring, and you see that this size and this size is much brighter than this side and that side. Also in this case, we have this and that part being brighter than the other one. So that's why we call it a pseudo-ring.
So they are like closed spirals.
There is a ring because let's go back. There is a ring because you can see that here it is something that it is all the way brighter than the environment. Here you see all these boxes that are drawn here. But what I want to say is that they are not, it is not all the way here red, for instance. Here it is very weaker than in this part. And you can see that also here in the galaxy. This and that part is brighter than, let's say, this quadrant and that one. So it's not homogeneous. That's why we call it pseudo-ring. Now, a feature that it is discussed in many papers who are in studies that deal with the central region is the expectation of the appearance of a leading spiral. Now, all the other spirals that you have seen is trailing. I mean, you know that the spirals in galaxies are trailing. So if we look at these two cases, in this case, the galaxy rotates counterclockwise, opens in that size, in this one clockwise, and these are called trailing spirals, okay, because the maxima trail as they unwind, starting from the center of the galaxy outwards. This is the way that the density waves in galaxies propagate. There are also theoretical studies on that, and some observational support also exists. This is the usual case. The density waves in galaxies are supposed to be trailing. Now, if they open the other way, for instance, look here, the blue ones are trailing. This is the sense of rotation of the galaxy. So this is the trailing spiral. In the innermost case, the analytic theory, the let's say the linear or almost linear, let's say description of the density wave tells us that due to the change of the sign of the of the radial velocity, here it would be expected to have a leading spiral feature. You see the red one. And this red one should be there according to the theory, but it is almost not observed in galaxies. There are some cases, but you have to try really hard to find it in images of galaxies. And for instance, here in the right one of the two images of the galaxies, here in the right hand side, you see an image that was published by Preben in 2003, where you clearly see a leading spiral. So here I have told you already that this is the way of rotation in this galaxy. Clockwise, here's the trailing spiral, and the innermost kiloparsec, let's say, here you see clearly defined a leading spiral, like in this case. Just imagine that we have opposite direction of rotations in the figures. Okay, okay, this is the clearest one. And ironically, this is not in gas. Okay, it is also young stars in gas, but it is supposed that the observation have been done to observe the old stellar populations in the near infrared. But this is exactly what one would expect to see much more frequently. And why we do not see that? The most common explanation that one can find is due to mainly to Francois Combs, and you can see that here in this. Oops, we have some problems here with back here. We don't have a mouse, right? No. Okay. Okay. It's because in the center there is a black hole, and if there is a black hole in the center, then this the shape of the rotation curve of the galaxy changes close to the center, and then this is enough so to let's say to keep the inwards propagating wave being trailing even closer to the center. This is the explanation that it has been proposed and supported also analytically in some cases. This is a nice figure that describes exactly what I'm telling you. So, okay. Here is exactly, I have already told you what the solution, the proposed solution was. Here on the right hand side you can see what happens. So here, the upper figure, this one, it is what one can get just by calculating the resonances in a galactic disk. And whenever a bar is present, the omega minus kappa half curve, the one that points to the inner Lindblad resonance, is as you see over there. The pattern speed is indicated by the red line, and so you can see that this is the straightforward way, the fast way to specify the extent of an H2 region. If we have an inner Lindblad resonance, then shows that we have an inner and an outer inner Lindblad resonance, actually this point and that point. Of course, this is not very accurate because all these estimations usually use just the axisymmetric part of the potential, but we are studying the bar. For us that we have worked all these years with the orbits, it's relatively easy to find. We calculate the orbits, we find the extent of the x2, x3 loop, where there are these orbits that are perpendicular to the bar, and then we can point exactly where this region starts and ends. But okay, this is what we mean. So whenever the black hole is added in the center, you see how this local maximum here is going up. Here is not even included in the figure. This brings the inner resonance almost to the center, and this is exactly the environment in which the leading spiral is avoided. Okay. So what we did now, we have models in our hard disks. This is one of the most popular one. It is a typical Ferrers bar, as you know, studied from many authors. Back to 1992, Leah Athanassoula did two papers in the same volume of monthly notices, one describing the orbital dynamics and then the gas responses of this Ferrers bar. The Ferrers bar behave very close to what we expect in galaxies. That's why they are popular. Of course, there are 2D models in that case. Okay, the gas is on the equatorial plane of the galaxy. You see the description on the right part of the transparency over there, and the left side you see the axisymmetric components on top of which the bar is placed. In the table that it is at the bottom of the figure, we see the main parameters that we varied to study the response of the gas in such a case. We assume just an isothermal gas. We don't even include the self-gravity of this gas, and we try to see the tendencies under this set of parameters for building, for having one or the other central morphology in the models. And just look at the A over B shows us how elongated is the bar, or the two semi-axes of the model. This RL is the point of the unstable Lagrangian points, practically how close to co-rotation they are. Then the third one just tells us how strong the bar is, and the fourth is R with subscript C, what is the central density of the model, and then the pattern speed, which could be also avoided because it comes from all the others. Okay, this is the models that we have studied, and let's see what were the results we got. Let me also tell you something about the code we used here. In this case, we used this RAMSES code. Some of you know that and have used maybe also this RAMSES code is a Eulerian scheme. This is the properties of the isothermal gas with the adiabatic index 5/3. And for each model, we studied three cases. They were different in their sound speed, so cold, warmer, and hotter, let's say, or whatever you want. 210 and 20 kilometers per second were the parameter that we varied in our gas. But let me tell you also that, as I said in the beginning, this was part of Stavros' master thesis, and during this work, we did also calculation with SPH. We compared the results for all models that had n equal 1 index in the Ferrers bar density of the models in LIA, and we were satisfied with the comparison. Okay, the two codes, hydro codes, have advantages and disadvantages. We can discuss it later. We can look at a paper that we already had published from the thesis of Stavros. But okay, we are satisfied, let's say, from the comparison. Here we use the Eulerian code, also popular code RAMSES. Okay, but since we are here in this institute, we do not avoid the temptation of calculating also the orbital dynamics. It goes very fast in our case. And how do we did that? Of course, we have autonomous Hamiltonian that describes the dynamics rotating with omega b. The phi potential is our Ferrers bar. And we did that because we wanted, after all, to find out what part of the response is determined by the potential and what part of this response is due to the hydrodynamics that we impose. So we did a parallel study for all our models. And also, that is very important, we also examine the stability, of course, of all these families of periodic orbits we find. We have looked what kind of quasi-periodic or chaotic orbits we could find in the environment, etc. You will see the results in a while. And here is the fiducial case that we use, as it is a general a model that has a lot of nice features. So all the rest we study as deviations from the response of this model. So here you see just in that case that we have this inner and outer linear structure, and that here in the central 1 kiloparsec region, it is let's say 10% the perturbation of the force and less as we go to the center. That branch here, here it is 10 to the minus 1, so it is, let's say, 10% and less. Okay, so let's see what is the orbital background in the central region. We do have the X2 orbits. For those of you that you are not familiar, I believe that everybody in the audience here is familiar with that. The X1 orbits are the elliptical-like orbits that support the bar, and the other very important family is the X2 that are perpendicular to the bar and that are in the central region. You will see all these terms that you will hear or find in papers, X2 region, inner resonance region, etc., are almost the same. Okay, and here it is the characteristic which gives the initial conditions of the families of periodic orbits as a function of the energy, or precisely, more precisely, the Jacobi constant. And you see that in this area here we have this loop. This lower branch is the stable X2 family, and the upper one is the unstable X3 family. And here is the Anon index for this all these families that are in this region: X1, X2, X3. You see that in fact they do not change stability, and we do not have also some tangencies or intersection with the upper and lower axis, so that we try to find bifurcations. X4, the retrograde family, may have one. We do not take the effort to define this orbits. But practically, this the conclusion out of this orbital study is summarized in this Poincaré section that you see in the at the bottom of the transparency. We do not have practical chaos. That's the point. Here is X1. In this case, it is not even X2. Here it's even closer to the center. here. But even in the, if we have taken an energy over there, we have the x2 and then the x3 here. But all these are invariant curves, you see. There is no chaos in this model. Okay, yes.
This loop always between the two inner linear resonances. This loop of the X2
This
and
one
X3
remain. This
is
one,
between
this loop.
the inner linear resonances.
Yeah, these are the two families of the inner
The energies
resonance.
are
The energies,
always
yeah, if we would like to
between the
be
inner
accurate where the inner Lindblad resonance and the inner and the outer inner stars, we could point at this and that energy, or if you go to the unknown index, to this and that energies. Okay, so there were no surprise. This is what I want to say, which is not, I want to emphasize this one, it's not in all kind of models the case. We have to try to study, and we have in mind to do that as soon as we can. We have models where there are other families, like the 1-to-1, and we have bifurcations, and we have other things like that. These are usually encountered in potentials that are estimations of the potential coming directly from near-infrared observations. In 2-3 cases, we had similar responses. Close to the center, there is much more interesting orbital structures. However, this is the typical case, I can tell you. This is what we have to try to understand, and all the others will be deviations. But have that also in mind. And staying for a while also again to the orbital dynamics, look back to this paper by Kontopoulos 1979 here. There are some regions where there is orbital crowding. One very interesting one is at the outer part of the H2 regions. Here the violet drawn are X2, the black are X1s, and see that we have usually intersections even of the X2 families by themselves. So you see here that to find an X2 orbit that does not intersect another X2 orbit, we have to go to this number 5 here and have this orbit. And here up, here and down there, we have crowding and intersection of orbits. Now we can do that. We are in stellar dynamics, in orbital theory, okay? And then there is another one, another crowding that is very close here. This corresponds to the inner Lindblad resonance. So this is the orbital background of the model we study now, this fiducial case. And let's see what does the gas do. From left to right, we have the 2, 10, and 20 kilometers per second responses in the gas. And you see that, you see several things, but in the left and central panel, first of all, here you have a kind of ring or pseudo ring, if you want, elongated. Then the leading spiral was there. Here the ring shrinked. Well, we can still speak about a pseudo ring. The leading spiral feature was still there. In the 20 kilometers per second case, however, then the dust lane is coming here. We have a ring much closer than that one. And here we have some over densities along the ring, and that's it. No leading spiral. Or there is something, but it is very weak. Look here. If you see this isophos, something is tending to be formed, but we really tried very hard to know this iso density. And a nice thing is also here, I like very much this over densities here, because there are papers that speak about these over densities close in the nuclear region of these galaxies. The other thing that I wanted to also to show you here is that, look, in the very central region, here is the bar coding of the density. The yellow is the largest, okay, the dark blue is the lowest. Here we have always a lower than the environment central region, see, always here. That's it. And to have also a feeling about how the flow is, we have taken a slit. This is the case with 10 kilometers per second, so that we have the leading spiral. And you see that along this red slit that we have here, when we have the intersection with the dust lane shock, which is this tiny overdensity over here, the blue one shows the density, the surface density, and the orange one curve shows the component of the velocity along the slit. Okay, so here you see that the velocity is coming from that point to that point. So here we have a shock. When we enter the region and we have this density peaks here and there is this and that one, we do not have such variation in the density. And then that two peaks are the ones that correspond to the leading spirals. Here there is something that happens, then it goes to the center, and in an antisymmetric way, it goes all the way. So the main shocks are always outside the central region. Here we have started to discuss if these variations can be described as shocks or not. Remember, we have in this case 10 kilometers per second sound speed, and the leading spiral is there. We also tried to look at this, something that is also interesting to see when these features are formed. And for technical many reasons, we did not give the perturbation abruptly in the model. We have a transient period where the perturbation grows from zero to the desired maximum that lasts 3 pattern rotations. And we have seen that the responses also during this preliminary phase were similar. So 2, 10, and 20 kilometers per second lead to these responses that you see here. Density. Here's the color coding. Yellow is large. Okay. So this is the response during the growing phase. Something with the camera? Okay. So, okay, I have already, here I summarized the main findings that are related with the fiducial case. So that the first one I want to emphasize that when we have put 20 kilometers per second as sound speed in our models, then we couldn't observe, or we couldn't observe that clearly the leading spiral. That means that at least the gravitational potential by itself does not determine if the leading spiral will appear or not. And also from this series of model, and as you will see later, I underline the presence of the low density region at the very center of the model. Okay, we will discuss about the similarities with real galaxies at the end of the talk. So let's see, when we go to another model, this is a model where the bar is rounder. So the ratio of the two axes of the bar are closer to 1. We have a round bar. And this is the result here. What we, in the cold case, in the 2 kilometers per second, we could see the leading spiral feature. It was there. Here we have a different construct inside, so just to convince you that it is over here. Then when we went to the 10 kilometers per second sound speed, we could more clearly see something that also exists over here, but we need to overdraw isophotos, etc., isodensities, etc., to show that the presence of these tightly round spirals. And also, when we go again to the 20 kilometers per second, we forget more or less what we have seen in these two cases. And here we have the continuation of the dust lane shocks in the main bar, coming, curving, and coming to the closer to the center. They give also two density peaks here, and then in all cases, the central region has a lower density than the environment. Now over here we can see the orbital structures in these cases. As we expected, due to the imposed potential, we had much more round constructions, and round orbits and whatever you can build with these orbits tend to be related with these tightly round spirals. We have seen that in the past, this response, and I will discuss it again here. This is what I told you. Again, just remember that when we go to 20 kilometers per second, the response changes. So we have two that are in some degree similar, 2 and 10 kilometers per second responses, not exactly the same, of course, but have much more between them, much more similar between them than what we find when we have the warm case. Okay. Then another case that we studied, the bar was weak. The amplitude of the perturbation, if you want, is much less than in the other cases. And then we found that this weak bar response and the round bar response were very similar. Again, here, look at the 10 kilometers per second model, that we have the appearance of these tightly round spirals that are going all the way towards the center. The logarithmic spiral that has as a property to have the pitch angle constant all the way. I couldn't say, for instance, if this is a logarithmic or an Archimedean spiral, which has the property that between along an axis they have equal distances, the maxima of the axis. But again, also in this weak bar model, what we see is that in the 20 kilometers per second, on the screen here it's not that obvious. Unfortunately, we have resolution problems due to the projector, but in the screen here you can see that here we have a very clearly tightly round grand design spiral that goes to the center. This is logarithmic. This one is also logarithmic, but with much more smaller pitch angle. And then again, at the center, the low density central region. Okay, then we did something else. Okay, since we find in all cases that we have a low density region in the center, we tried another model where we put gas in the center from the beginning. So we increase the central density. So here is the corresponding rotation curve. Look how here the environment here changed. This is much closer to the center. The forces are similar like in the other cases. So let's see what happens when we study this model. The orbital dynamics is like that. I think that what one has to remember from this figure is that, again, closer to the center, the orbits, this black one here, all the black orbits are x2, the red are x1. You see also an x1 even closer to the center. After a specific radius close to the center, they become almost circular. So this is the orbital background in this model. And what we find here, okay, here again we have the pseudo ring, we have the region which is clearly with lower density than the rest one. Here it's not that clear if it is or if it is not. Clearly it is. It is, but it is not that obvious like that in the center. But look what happened with when we go to the 20 kilometers per second. Then the gas, the one that we pushed by ourselves, we put gas there from the beginning, stays there. Or we find that it peaks closer to the center. Is there a question?
I think I figured it out. Okay.
Okay. Maybe this next figure helps us understand what happens. So again, we have, this is the 20 kilometers per second case. Again, we take the slit and we see, okay, that when we are here, here and there, then we have the shocks. But when we enter here, there are no shocks, definitely. And all these peaks are something like, again, like trailing spirals, but they are that close one to the other, and so small the variation of the density that visually gives the impression of a central disk that is formed there. And now we have again some kind of twin peaks, but these two features here and there, but they are almost close to the center. So if we go to less than, I don't know, very close to the center, it is there is a small density minimum again here, but it's negligible. In this case, we can say that the gas was brought closer to the center, and imagine that we do not have, for instance, included in our modeling self-gravity. If we had self-gravity, I'm sure that this would bring this all the way to the center. Why is this case here interesting? Because we do not have assumed any black hole there. We tried to put another massive component, of course, and we put another massive component, this high central density close to the center, but it is not a black hole. And this can bring gas close to the center without invoking the black hole, but by increasing the temperature, making the gas warmer. And okay, I have told that one. We tried also to understand to what degree the results depend on the relative forcing, that means in the potential in the bar, and in what degree it's hydrodynamics. We did this kind of experiments, let's say. We considered very, very weak bars, almost not existing. So practically dealing with the bar is there, but it's very geometrically. These are response models. Whatever we want, we put in, so we can control what is the response. And we have seen a case where we had the high central density, and the other one that we didn't have the central density. What we observe here, we have increased very much the contrast so that we can describe the features. Of course, the bars, when the bar is there, brings much more gas closer to the center. The central region of these modules, however, are characterized by the presence of tightly wound spirals. Whenever we started with the high density was there, as you can see here. But the problem is that we do not have here shocks in this region. So how is all these features built? It is because the accumulated gas with the time is accumulating and pushes whatever has not to go and pushes the other gas closer to the center. This happens also in this case. This happens also in the case where the bar was present. I just want to show you also one case that we studied where we avoided put in from the beginning in the model an inner Hilbert resonance. How can we do that? Just by increasing the pattern speed. We increase the pattern speed, and then we try to have initially all the other parameters the same. You see that we speak about two models is because we repeated the calculations for a case with lower central density, but the results were almost identical. So the difference in that case was the appearance of a four-armed response in the bar, which was due to the different location of the resonances, was practically the bar itself. There was no inner Hilbert resonance in this case. The extent of the bar was close to the 2 kiloparsec frame that we had in all figures that I have shown you until now. And you can see, again, better described in the 20 kilometers per second case, sound speed. Here you see this four-arm response that was present. Again, even if there was no inner Hilbert resonance, the central region had a lower density. Let's look also what happened in this case with the orbits. The orbits are of this kind. All orbits that are in the area you have seen in the gas response, which is corresponds to this blue frame here, are like that, closer to the center, because around. Look here, there's however a difference. This, sorry. The difference is farther away from the center of the galaxy. I repeat, we do not have here an X2, X3 or other families. And here is that at the 4-to-1 resonance now, the behavior is different. So the X1 orbits is coming up, and whatever new family is bifurcated over there is below it. This was the only model that this behavior was like that. Usually we have this red stuff here being on that side of the X1 orbit. Old papers describe exactly the properties of the two cases, the orbital dynamics, the type 1 and type 2 gaps at the 4-to-1 resonance. Since we do not have any 2-to-1 resonance, inner 2-to-1 resonance, link-blood resonance, we try to understand why this four-armed response by looking at the environment of the next even resonance, which is the 4-to-1 in that case. Okay, here is. Now, let me try to summarize and point to issues that should be discussed or are open issues or whatever ideas one can have. Well, it is obvious that we have structures in the innermost kiloparsec whenever we have an inner limit resonance, any kind of structure. Whenever there was no inner limit resonance, we haven't seen any structure closer to the center. However, the whole response was different in the last model I have shown you. What we have seen is that when the sound speed was low, we could point to correspondences between the orbital dynamics and the response in the gas easier than when we increased the sound speed. For instance, if we go to the models with 2 kilometers per second and 10 kilometers per second as well, we could see that we had a ring. The ring was always smaller, let's say, than the extent of the X2 orbits, but were closer to the extent of the X2 orbits as when we had a 2 kilometers per second sound speed in the models. When we started increasing the sound speed, we had deviations from that behavior. So it was, I'm speaking always for the central region, right? Not in the main bar, it is another world. In the innermost kiloparsec, then we couldn't point to dimensions or things that had a correspondence, or we could do that much more difficult. Then, however, this 20 kilometers per second had many nice features. We knew that also from the past that due to the sound speed of the gas, the dust lane shocks in the main bar were much better described and all that stuff. But we see that if we look to the responses we find in these simple models that we are studying and to the images of the galaxies, we find corresponding features between these two. I mean, the 20 kilometers per second case and the images of the galaxies. For instance, in this case, you see we have all the dust lane coming all the way bending inwards and staying there. Here we have all the way they are coming bending inwards and they stay there. You compare, you find a better comparison, let's say. I don't generalize, but the tendency. Whenever the 20 kilometers per second is assumed and we get a response, then this morphology is easier. It is easier to find corresponding morphologies looking at images of galaxies. Yes.
Observation, can't you have characteristic of the like temperature, for example, in these gas?
Oh, it depends what you mean temperature. This we have an isothermal model there. It's very simple, our model. Then in real galaxies, this.
For example, if you have a spectrum with a Planck law, for example.
No, it's exactly what I tell you. There are several kinds of procedures, phenomena, or whatever you want to say, that are happening in the central region. The gases, I don't know what kind. There is star formation. There is many things. It's very difficult to point. I would would like to go the other way around. Let's see if what this 20 kilometers per second really means for the observations, not trying from the observations to see what these models give, because they are very simple models and give also tendencies. Either we should increase the complexity of the models, but I'm not sure if we will just, let's say, be satisfied with all these details that we can find, or a general tendency. If we have better responses in warmer than in colder isothermal media, ISMs. So also another thing that, speaking about comparisons, is that these twin peaks that we always find, and they appear as the dust lanes are coming here and trying to form these rings, are always there. And we have seen that in the case where the gas went all the way to the center, then these two, not yet. They were coming very close to the center. So this one is also very interesting. So whenever we have low perturbations, very weak bars or non-barred cases, etc., or round geometry, round topologies, then we see this association of tightly round spirals with these properties of the potentials. We knew that from many years ago, that when we were trying to model non-barred galaxies, and then we had did some assumptions about the strength of the perturbation, trying to model specific galaxies which have this very tightly round character. So SA, lowercase a, SA spiral galaxies. So this kind of type. These were much better described. These were the models that we proposed with very low amplitude. So this one, all these models tells us that anytime you make the models rounder or you decrease the perturbation, this tightly round appears. So this is also something that would be very interesting to be re-examined if you want, that points that the let's say the self-consistency of the models could be towards this direction. And here is something that also, here. Look, here is one of the models of the past. Here was for a specific model, but under the same assumptions. You see how tightly round spirals are created, and in this case we're in agreement with the galaxy we were trying to model by that time. And the same happens also to the gaseous responses. So the tightly round spirals in galaxies were modeled with low density, low amplitude, let's say, perturbations. Now, this is also something interesting. I said that I was speaking about the relation between orbital dynamics and features observed. The leading spirals in the models, now let's come to the models, where are the leading spirals in these galaxies, I don't know. But it is nice to see the correspondence of the distance between the orbital crowding that we found in the model. Here's the fiducial model that we had in the beginning, that you see here in the right-hand side. And you remember I was telling you about the crowding here and there. The crowding here and there, at the distance at least, are almost the same distances that we find this density maxima in the gas, here and there. This corresponds to that and that crowding. So it is obvious that when we go to colder models, then the relation between the orbital dynamics and the gas responses is closer. We find that. The point is, the open question is if this is the right set of parameters to model the gas, since in the 20 kilometers per second, we find results that resemble morphological features that we encounter in the images of the galaxies. Okay, now, I underline this model that we had the high central density in the beginning, and that for the warm case with the 20 kilometers per second, we could have gas very close to the center of the galaxy without any further assumptions, and that this was done having as shocks mainly the shocks that are in the main body of the bar, and then this gas was coming and coming and coming, and then pushing whatever they have found there and pushing closer to the center. This is the mechanism that has produced all this, the disk here. And I think this is what I want to tell you. If you have questions. You and the rest of our colleagues and friends that are followed here. So one question here, yeah, James.
We're a little bit confused with the isothermality assumption. Can you have shocks with isothermal?
Yes, of course you can have. You have an initial medium, and then you have, let's say, let me describe you the shocks in the main bar. So as you have seen that the one that you have is coming, the gas is coming, then this the shock loses angular momentum, goes down, and this is a shock. So you have differences of many tens of kilometers per second, assuming a sound speed of 2 or 10 kilometers per second, or 20 if you want. Doesn't mean that it is the same from one to the other side. Then you would have just, let's say, some gas that was going circular way around the center of the galaxy. We don't have this kind of motion. The orbital background, the potential, in other words, bends the material, and then it is shocked at the leading sides of the bar. That is where it loses angular momentum, and the shocks can be found. We find the shocks. We see that we have these jumps in the velocity.
We have a different understanding of hydrodynamic shocks. If you change the density, you change the pressure.
And all this change here. Why?
If you change the density, you should. But you describe them more as a break in the velocity.
It's the best way to visualize it, let's say. Well,
so you said you have found some correlations between the amplitude of the bar and the, for example, pitch angle of the nuclear spiral. And when it is weak, it is more tightly wound. And maybe when it's very weak, you see rings and not spirals.
When you have this, if you have a weak perturbation in the center, that means that you are closer to the axisymmetric model. That means your orbits are rounder. Okay, this is the environment, and what we see there is the presence of tightly round spirals. In this case, this is the association. If you have this very round orbits, then in the gas response you see these spirals. What is I'm not really understanding very well is that you have almost circular orbits one inside the other. You do not have, whenever you have a spiral potential, even the weakest perturbation, then you will have this precessing ellipsis thing. You don't have it here, but still you see spirals. So I think that the hydrodynamics play a role there. For
and have you seen any correlation between the pattern speed and the pitch angle of this nuclear spiral.
The pattern speed for all the cases but one was almost very similar.
But
the one that we changed so that we avoid having the inner lipid resonance, then it had a totally different response. We had 4.
Yes, I see. But
and I believe that this relates with the type 1 gap that is observed in this model.
Yes.
All the others had type 2 gaps.
But if you still have inner resonances, and you check if you still have inner limited resonance and you change the pattern speed, maybe you will find some correlation between
but since the model is the general model is the same, the variations are not. We didn't check to tell you the truth, but the variations are small. So we have to see a clear difference. You have to do something more dramatic so that to increase the.
Yes.
So all the other are similar pattern speeds, same order. So if it is a few kilometers per second per kiloparsec, more or less, I cannot say.
In grand design, certain correlation. So maybe.
Yeah. Remember always that this is the central spirals that have their own world. This was also what we want to see. What is the how can we understand the dynamics in this area, where in a real galaxy, of course, you have the amount of gas as it is moving towards the center of the galaxy increases also with the time, and then you have. That's why I told you that when we will consider the self-gravity of the gas as well, I expect to see differences. Right? Here we didn't have that. So the gaseous component becomes much more important than you have it, let's say, at the 4-1 resonance or closer to co-rotation on all that stuff.
And the pitch angle of the nuclear spirals with the pitch angle of the outer spirals?
Oh, it is totally different because the outer one, it is a bar, so 90 degrees pitch angle. And then it goes all the way down, the shocks, the dust lane shocks.
Another world there.
Yeah, it's 90 degrees, it's a bar. Except of the 2 models that we have checked almost axisymmetric, where you didn't have anything farther away. But in the center, you had the nuclear spirals. That means that this points towards a hydrodynamic origin of these features.
There was important for you the sound speed in the galaxy. Have we observed in some way the speed of sound in real galaxies, or is it something that you set as a template?
Yes. So we just use it as a free parameter. I cannot tell you what is the relation of. I believe that one needs much more complicated modeling for saying something very specific about what you ask. Now here we are looking for tendencies. We have a very simple assumption: an isothermal gas, no self-gravity. Let's see what happens. We will go the other way around. What means this 20 kilometers per second as a tendency? Warmer gas gives better results. Is this something that we have to assume for galaxies and then we try to say, but no, it's a very simple modeling. Observers can help us, but if you start, I have discussed it with observers, they will start telling you, oh, but you don't have star formation there, oh, you don't have the self-gravity of the gas, oh, you know, it's complicated, dust plays this and that. It is a whole world. Here are just tendencies, what we describe. But tendencies is something like a zero-order approximation in what you want to see. And that's why we take the effort to do this.
Kind of related with that, first, in the beginning, did you say that we don't observe many leading spirals? One explanation could be because of black holes, right?
Yes, this is what the explanation that one can find in the literature is black holes.
Kind of inject some energy in the surrounding, increase the sound speed, so be in accordance with what
can be a way out of all this stuff. Why leading spirals are not frequently observed is because all galaxies have a black hole in the center.
So, like, you don't explicitly put a black hole in your model, but you increase the sound speed, which would result.
Look, even from what we do here, it is that shows again the tendency.
Yeah, so the tendency is in accordance with
The larger the central density, then the more difficult it is to see the leading spiral, let's say. Also, we didn't have put a point mass there and do the calculations. We have taken a kind of, we increased the central density of the
I'm
model.
thinking more like rather than densities, the energetics.
Yeah,
And
okay.
black hole if
It can change the environment, yeah, okay. But always we have to think about the scales we speak here. Now we are coming close to some tens of parsecs from the center in the best case, while certainly a black hole which first will affect even smaller distances from the center of the galaxy. Now, of course, what can it's also influence also the orbital dynamics, so everything. But where we reach without assuming a black hole, it is some tens of parsecs. Okay. So, okay, will be affected certainly with all what you said, but not, let's say, I wouldn't say that 100 parsecs from the center or 200 parsecs from the center will be affected so much. I don't know. Just a feeling of some questions from people that are online connected.
Αυτό υπήρχε από την αρχή όμως.
Okay.
Ναι.
Let's see this.
Και ακούμε τον ήχο.
Okay. 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 Then there are no other questions. Thank you.
Stop. Πού είναι το end? Πάτησα μόνο. Θα πάτε more. Πάμε εδώ πάνω. Stop recording.
Όχι, ευχαριστώ.
Είναι και end meeting πρώτο, αλλά είχαμε κάνει. Πάμε. Πάμε, stop. Stop recording.